Okay, so I will say a few words about the characterization tools that we have at Irig. So let me move on to the next. So Irig stands for Interdisciplinary Research Institute of Grenoble. It groups about 1,000 people involved in fundamental research. And it comes mainly from the Fundamental Research Division of the CEA. And the subjects of the people ranges from health, biology, chemistry, cryogenics, and physics. It's a big institute with 5 departments and about 10 labs. And today I will talk mainly about the activity of the Mem Lab, which groups the characterization teams, especially in the field of material science. So the key figures of this Mem Lab are illustrated on this hexagonal paving. So we have 60 people located in 6 teams, each with an expertise on different techniques. For example, the LCM lab is specialized on ab initio calculation and simulation, like DFT calculation and so on. The LEMA is the Electron Microscopy group. I will speak a little bit more about it after. We have a magnetic resonance group specialized in standard NMR techniques, but also in dynamic nuclear polarization. And we have people doing X-ray and neutrons, so lab X-rays, a little bit like what Eric Mossang showed you, and we have collaboration with them. And we have synchrotron and neutron groups that operate CRG instrument or CRG beamline at Esrf and at the ILL. So they specialized in surface techniques for the synchrotron group, and for the neutron group, they specialized in inelastic and magnetic scattering. So I will focus today on 2 techniques where we have some new things to say and performance gains inside. The first one is about focused ion beam scanning electron microscopy nanotomography. So it's done within the LEMA team by essentially Pierre-Henri Junot and his collaborators, and they are located at the PFNC, which Olivier Renaud has already spoke about. And the second point I will make will be about scanning MicroLaue diffraction, and this is done by the NRS team at the CRG BM32 beamline. So first, focused ion beam nanotomography. So this is a technique which is a real tomography technique. It means you cut the sample and you image the cut surface by scanning electron microscope. So it has the advantages of scanning electron microscopy, that is both a high resolution and a wide range. So in a range versus resolution a graph, it will occupy the central square with a large area, and it bridges the gap between X-ray tomography at large size and medium resolution, and electron TM tomography, which has a very high resolution but a lower range. Okay, so next slide is where is it? Okay. So a FIPSEM is looks like SEM microscope. This is an example of one of the 3 FIPSEM that are available at the PFNC. You have a beam to do the tomography. This is a gallium beam, and you have an electron beam to image the sample. The applications in the field of the Nanoelec IRT are about semiconductor dot layer interconnects or vias in electronic device, photovoltaic and optoelectronic devices. So I have here an image of an IR photodiode that has been fully imaged in 3D, but I cannot show you really the tomography because it's a very heavy file. And the development and perspectives in this field are about we installed cryogenic sample holder that's useful when you want to reduce the damage and stabilize your sample. As I told you, it produces huge amounts of data, and it can be when you have both a wide range and a high resolution, you make really high volume data, so you have to find smart techniques to acquire the data. So that's why people have worked on compressed sensing techniques. And in the future, and in collaboration with the CMTC you just heard about, we plan to replace one of the instrument by a gallium-free FIB beam, which would be a plasma FIB, which has the advantage of producing less sample damage, because then you don't have problems with gallium contamination, alloying, and it may allow also faster ion milling. Okay, so now I will move on to the second point I wanted to make, which is about scanning MicroLaue setup at Esrf. So the Irig and the CNRS run 5 CRG beamline at Esrf. They are located on bending magnet or wiggler sources. There are several instruments there to perform X-ray scattering, for example, reciprocal space map, grazing incidence scattering, or X-ray spectroscopy like XANES, EXAFS, and so on. So the SRF allows the use of high energy, and it's very well suited to study buried system, to study real samples with real in situ operando sample environment. So now let me move to the next. So the Laue setup is very simple. You have you shine a wide beam to a sample and you collect the scattering image. And the advantage is that you make a full use of the whole spectrum of the bending magnet. So you have flux, you don't need to rotate the sample, so you are fast. And you take an image at each point, so you have a full information in one shot. You can then, if you scan the sample or if you scan the beam, you can make images of the structure of your sample, and this is illustrated here on a few examples. The first one is a buried series of bubbles that are produced when you implant at the heart of silicon that have been implanted. This is a collaboration we have with the Soitec company. And here on the right, you have the image of a strain membrane, which has a cross shape to concentrate the stress at the center of the cross. And you can see, comparing the stress and strain measurement done with MicroLaue to finite element modeling, that you have a nice correspondence for all the components of the stress tensor. You can combine X-ray with other techniques, and this has been done here. For example, combining the MicroLaue with light collection, so it's so-called the Xiol technique, and It has been used, for example, on an array of gallium nitride LEDs. And the nice thing with these techniques and with X-ray in general is that you can then correlate the structural information that you get with X-rays with the optical or the other properties of your sample. Here, the optical properties, which of course is important when you have optoelectronic devices. The developments for the MicroLaue is an improved high-speed scanning to really do 2D imaging and maybe 3D imaging in the using other complementary techniques. So you can combine with other measurements like X-ray fluorescence or light excited optical luminescence. You can do 3D mapping that is not only in X and Y, but also in the Z direction. We have, thanks to the EBS, the new Esrf source, we have an improved resolution. We can go now to 100 by 100 nanometer beam size. And of course, as for the FIPSEM, we have also to improve the data management and to improve the data treatment. This is a very important issue in characterization these days. We have high volumes of data, so we have to provide tools to really fully exploit these data. Okay, so that's, I think, all about what I wanted to say. So I thank you for your attention. I've put here the contacts that you can write to, and of course, please don't hesitate to contact us, visit our website, contact people directly if you're interested. Thank you.